All right, welcome. Today, we're going to pull back the curtain on something that's honestly one of the most complex and fascinating journeys in all of science, how a brand new medicine actually gets made. We're going to break down that whole process, from just an idea in a lab all the way to that pill in your local pharmacy. I mean, really think about it for a second. The last time you took an aspirin, or, your daily prescription, it probably just felt normal. But the story behind that little pill, it's an absolute epic of science, patience, and frankly, some incredible odds.
Let's just start with a number that kind of sets the stage for everything we're about to talk about. 10 to 15 years. That's how long it takes, on average, for a single new drug to make it from day one of discovery to your medicine cabinet. A decade and a half? It's wild.
So how on earth is that massive chunk of time broken down? Well, it's definitely not a straight line. It's more like a highly structured, super intense marathon, with each leg of the race taking several years.
And this timeline really shows you the main stages of that race. See, it all kicks off with discovery and preclinical research. We're talking years in the lab, working with cells and animals. Then, it graduates to the longest and most difficult phase, clinical trials in humans. If, and trust me, that's a huge if, the drug makes it through that, it then has to face a super rigorous FDA review. And even then, the story's not over. After it's approved, it's still being watched for safety in what they call phase 4.
Let's zoom in on that middle part, the clinical trials, because this is where most potential drugs just fail. It's a true gauntlet, a series of tests that get harder and harder, all designed to answer two basic questions. Is it safe for people? And does this thing actually work? What's so amazing here is just the sheer jump in scale. You start with phase 1 with maybe just a few dozen healthy volunteers. The main goal there, just safety, that's it. If it passes, phase 2 opens up to hundreds of patients who actually have the condition, and that's where you start really looking for effectiveness. Then, if you're lucky, you get to phase 3, a massive, massive undertaking with thousands of people to confirm everything on a huge scale. But hold on. Long before these gigantic, super expensive human trials, scientists have to answer an even more basic question. How do you even know if a drug molecule can get into the body's system to do its job at all? It's a massive first hurdle to clear.
Well, to solve this puzzle, scientists use what you could almost call a secret code. It's a classification system that helps them predict how a drug might behave before it ever even gets near a person, which, as you can imagine, saves a ton of time and money.
And this code is built on two, surprisingly simple but absolutely critical ideas. First up is solubility. Basically, how well does a drug dissolve? Just think about putting sugar in your tea. If it just sinks to the bottom, it's not doing you any good. Then you've got permeability. This is how well that dissolved drug can pass through a barrier, like your intestinal wall. The classic example is water going through a coffee filter. For a pill to work, it really has to do both of these things well. And the official name for this whole framework is the Biopharmaceutics Classification System, or BCS for short. It's a really powerful tool that scientists use to group drugs based on those two exact traits we just talked about.
Okay, so this is where it all comes together. By figuring out a drug's solubility and its permeability, you can sort it into one of 4 different classes. And as we're about to see, each class has its own kind of personality and its own unique challenges that scientists have to figure out.
And here it is, the BCS matrix. It looks kind of simple, right? It's just a 4-quadrant grid. On one side, you've got permeability, going from low to high. On the other, you've got solubility. Every single potential drug molecule fits somewhere on this grid, and that placement immediately tells scientists what kind of challenge they're facing.
This table is a fantastic summary. You can see exactly how each class mixes and matches these properties. And that mix defines its biggest challenge. For example, solvation rate is just a fancy way of saying how fast it dissolves. And permeation rate is how fast it gets through that body barrier. This is literally the roadmap for making a drug work.
Okay, so let's meet the 4 classes, starting with Class I. You can think of these as the all-stars of the drug world. These drugs are basically the dream scenario. They've got high solubility and high permeability. That means they dissolve super easily and they pass through the body's barriers with no problem. They get absorbed really well, often faster than the body can even get rid of them. A perfect example is paracetamol, that common pain reliever.
Next up, we've got Class 2, and these guys present scientists with what we can call the dissolving challenge. So Class 2 drugs are fantastic at getting through barriers. High permeability, check.
but they're terrible at dissolving in the first place. For drugs like ezetimibe, the whole process gets stuck at step 1. It's limited by how fast they can dissolve. I mean, it doesn't matter how great you are at getting through a door if you can't even get out of your car, right?
Now, Class 3 is the mirror image of that problem. This one is the permeability puzzle.
So these drugs, like cimetidine, dissolve like a dream, high solubility, no problem there. But then they get to the body's membranes and just stop. They have a really tough time passing through because of low permeability. So the drug is dissolved, it's ready to go, but the whole process gets bottlenecked right at that barrier.
And that brings us to the last one, Class 4. This one represents the ultimate challenge for drug scientists. Yep, these drugs have the worst of both worlds. They have low solubility and low permeability. They don't dissolve well, and even if they do, they can't get through the barriers very well. As you can guess, this all leads to really poor and often unpredictable absorption. Drugs like bifenazole fall in here, and they are a major headache for developers to work with.
So we've gone from a 15-year timeline all the way down to this little 4-box grid. But why does sorting drugs this way matter so much in the real world? What's the point?
Because the BCS isn't just some academic thing you learn in school. It's a predictive roadmap that's used every single day. By knowing a drug's class right from the start, scientists can design the medicine to overcome its specific problem. If it's a Class 2 drug, they'll work on making it dissolved there. If it's Class 3, they'll focus on getting it through that barrier. This saves an unbelievable amount of time and money on that long journey to the pharmacy.
You know, understanding these basic properties doesn't just help us make the drugs we have now better. It opens up all kinds of new possibilities. And it leaves us with a really fascinating question to think about. As we get better and better at solving these challenges, could we one day see prescriptions that are tailored not just to a disease, but to the unique way your individual body absorbs things? Pretty amazing to think about.